In this unit, we're going to return to the foundations of integration as an idea or a calculation of area under a graph, and we're going to extend that simple idea to finding areas in slightly different ways, and also to generalize it into a third dimension when we start looking at volumes. We'll look at some classic volumes, and then we'll look at a particular class of shapes called volumes of revolution, which are generated by spinning a graph around some axis. And we're going to see how simple it is to develop integrals that represent the volumes of those shapes, and then evaluate those integrals to actually find the volumes. We'll start with the idea of area being related to integrals, though. If we look at this question here, write the integral that represents the area underneath the graph of y equals x squared between x equals 0 and x equals 2. The first thing I hope we would do is sketch a graph. That would be the graph of y equals x squared, the parabola, and we have an interval given, x equals 0 to x equals 2. And so what we're looking for is the area shaded in red here. From our study of integrals when we first started, we can say that that area, being above the axis, is all positive. That area is going to be the integral of x squared dx from 0 to 2. And I'll be explicit here and mention that it's x equals 0 to x equals 2. And we'll say that's the shaded area here. And that gives us a way to calculate this, remember, not at all rectangular area. About 5 weeks ago, all we had to calculate areas were rectangles and circles. Now we can find the area underneath any graph whatsoever, as long as we can perform the integration step. Let's do that here. So the area we want is given by the integral of x squared dx, and so the area will be the antiderivative, x cubed over 3, between 2 and 0. Then we plug in the upper, and plug in the lower, and subtract, and we end up with 8/3 square units. Perfect. So that area there is given by 8/3 square units, or has an area of 8/3 square units. Now that's not the only way we can find the area. Let's go back to the first principles where we developed this integral and see how that plays out and how we might be able to modify it. So if we had that same graph now drawn out a bit more nicely, let's go to 1 and then to 4. And that's x equals 2 here, x and y. What we actually built was, let's do this in green, a series of rectangles each with their own height, and we wanted to find the total area of these rectangles. And so the total area, let's actually do this in stages. One rectangle is going to have an area defined by its width and height. Height times width. And if we look at the shape of each of these rectangles, the height is dictated by the y as a function of x, times then the width, which is always a narrow delta x value. So the total area is the sum of the single rectangles. And for those who have seen summation notation, it jumps pretty quickly to adding up all the y values at a certain x coordinate times delta x, or knowing what we know about our function that y is given by x squared, we can say this is x squared times delta x. Now, we should be a bit careful here. These are all approximations because they're rectangles and not the actual smooth curve. But what we did next when we introduced integration was we took the limit as delta x goes to 0, or as the number of rectangles goes to infinity. So we use finer and finer and more rectangles. And from there we saw the conversion of this summation notation. Let's be very clear how where each of these parts comes from. if we're adding up rectangles of width delta x and height x squared, so each of these rectangles has a different height depending on the x coordinate, then we could get the exact total area as the limit of these delta x's goes to 0 or the sum has more and more terms, and we turned it into an integral instead of a sum. The x squared stayed identical, and the delta x is replaced by what we conceptualize as an infinitely thin dx. And then we can explicitly put our limits of 0 to 2. And that's where the first and last rectangles will occur. And that is what gave us the total area of the space underneath the graph. Once we have this integral based on the idea of sums of areas of rectangles to get a total area, then we could apply our theory from the last page, which, if you recall, was the fundamental theorem of calculus, which says that integrals are the opposite or can be evaluated by using the opposite of differentiation. And then we use that in the last page to find the actual area. The key thing for us now is this idea, this explicit idea of taking sums of things we want to add up and doing it with a finer and finer grid to get an integral. That's what we're going to be using throughout this unit. Let's explore that with the same example, but with a slight change. Instead of taking our rectangle slices the same way we did before, vertically, we're now going to take those slices horizontally. We should get the same area, obviously, because we're not changing that, but we should get to it through a different process. Okay, so what we're going to imagine here is taking our slices horizontally and having little rectangles like this. Okay, so now we have to think through, how does this tie back to what we've seen before? Well, one rectangle has an area of height times width, and the heights in this case are delta y. Let's do that right here. They're going to be very narrow, and when we think of what's going to happen when we use more and more rectangles, we're going to make them thinner and thinner. We're going to make them tiny little slices that are very, very thin vertically. So the height is going to be a small y unit, and the width gets a little more interesting. Now, if we think of this point, again, don't think of the first or last points. Those tend to be deceptive. Think of an intermediate point somewhere on the curve. That is going to be defined by y equals x squared, because that is our curve. The point at x gives us the y coordinate x squared, x squared. Or we're interested now, though, in somehow in widths, so x direction distances. And so we would recognize that y equals x squared is equivalent to x equals root y. Now, here's the tricky part. When we think of a point on a graph, we can think of x as the coordinate, but x is also the distance from x equals 0. When we say x is 1, that means it's 1 unit to the right of x equals 0. So we can talk about this distance here being the x distance. We can also talk about this entire distance here being 2, and this should sound a little familiar from the optimization problems and related rates. We can then find our widths. That width, of course, is just this distance here, which is the whole distance, that's always constant, 2, minus x. So if we say, what's my x coordinate? Oh, it's over here. What's the distance left here? 2 minus x. The bigger x gets, the smaller the width of the rectangles in the shaded area we're looking for get. So we're going to be using this idea of subtraction and some fixed distance related to x or y as we go through this unit. So if this isn't totally clear, take a look back at this, try to draw some diagrams, and see if you can put it together. With this width, we can now finish off our area of the area of one rectangle. Delta y 2 minus x. But if you look at this y, we have to remember that, well, 2 minus x and y's, we don't want to mix our x and y's. So what can we do? Well, we know that if we pick an x coordinate, we can also find the matching y coordinate by x equals root y. And so we can get the area of our rectangle as delta y, 2 minus square root of y. And then the usual sequence here would be to say, what's the total area? Well, the total area is approximately the sum of all those rectangles. We take the rectangles and we add them up. Now, we know that's going to be an approximation because the rectangles would be missing little areas, but we can say that's an approximate total area. The exact total area will be equal to the integral. So we replace the sum with an integral. We're going to move things around here to make it look a little more traditional, but that's all we're going to do. We're going to take the delta y, make it a dy, and we're going to take the 2 minus root y and just keep it as is. And then we're going to remind ourselves that this is an integral with respect to y, so we have to go from y equals what to what? Well, the first rectangle was down here at y equals 0. The last rectangle was at the top, and if x equals 2, then the top y coordinate would be y equals 4. So our integral goes from y equals 0 to y equals 4, all these slices. So keep in mind, it's a very mechanical construction of this integral based on the diagram. There's a one-to-one correlation between all the pieces in the diagram and what we get in the final integral here. The nice thing is that now that we have this integral, we can simply evaluate it, and we should get, let's go back one page, we should get 8/3 square units, because that was the area we developed or computed using rectangles that were aligned vertically. All we've done is represent this area in a different way now, but we should get the same area because that hasn't changed. Let's see how that works out. So we have the integral from 0 to 4 of 2 minus root y dy, and that's the total area. Well, that will equal the integral of 2 is 2y. The integral of y to the root y, well, remember that's y to the 1/2, will be y to the 3/2 divided by 3/2, and all of that between 4 and 0. And then we just plug in our upper limit. We get 2 times 4 minus 4 to the 3/2, and divided by 3/2 is the same as times 2/3. And on the other end with the zeros, it's really easy. It's 0 minus 0. Then we get 8 minus 4 rooted as 2, so this is actually 8 times 2 over 3, and that's 8/3. What have we got? 8 minus 16/3. And if you do the calculation in your calculator or put them on a common denominator, either way, you will end up with 8/3 square units.